All right, how's everyone doing today? Good weekend? You're quieter than normal, but that's okay. You can be quiet if you want. It's Monday. So I guess for us, it's clear sailing until the exam. We got nothing really else to worry about. We have just the material we got to cover. We're done with tests. Midterm 2 is 3, I guess, is behind us. We are in Chapter 8, and in Chapter 8, I just want to briefly recap the reactions we've seen so far. Okay, and that's because Chapter 8, the complicated part of Chapter 8 is just that there's a lot of reactions and conditions, which is different. Well, I guess you could say Chapter 6 and 7 have lots of different conditions that are only slightly different. Maybe these are a bit easier. In my opinion, 6 and 7 is the hardest stuff, and it gets easier from this point forwards. We did a reaction where we did hydrogenation. I'm going to give as an example cyclohexene, not hexene, butene. 1,2-dimethyl cyclobutene. And if we treat this with hydrogen gas in the presence of a catalyst like platinum, palladium, rhodium, or nickel, what will happen is we will get hydrogenation, addition of H2 across the bond, and we would say the stereochemistry of this addition is syn, meaning both hydrogens go on the same face, and if there's like a dimethyl like we have here, those two methyls will be cis in the product. We looked at some variations of this. We said that if you started instead with an alkyne, let's use palladium this time, then it will go all the way to the alkane. It's syn as well, although, you know, you're making a double bond, so it doesn't matter. Sorry, you're not making a double bond. So it'll add hydrogen twice. So you'd need 2 equivalents here of hydrogen gas, 2 moles for every mole of starting material. We had a variation of this, though, where we have a catalyst that would stop at the alkene to give you a cis alkene. And did anyone remember what the catalyst was called? Yeah, Lindlar's catalyst. And that's a palladium variation. I think it's palladium that's treated with quinoline, which is an organic nitrogen-containing aromatic compound, and lead acetate. But for you guys, you can just think of it as Lindlar palladium, and that'll stop at the alkene stage, and it'll give a cis alkene. If you wanted the trans alkene, we have another variation where we use sodium metal in ammonia typically. And this will give the trans product. Okay, so this reaction is called the dissolving metal reduction. And it's called the dissolving metal reduction because you start with chunks of sodium metal, and as the reaction proceeds, the sodium metal dissolves, becomes sodium plus, and the electrons are going to the alkyne to reduce it, and that's why we call it the dissolving metal reduction. So there's 4 variations of addition of H2, and then we went to addition of HX. So if you have something like this, we had a mechanism for this where you'd have initial, if you had, let's draw the bond out here. You have something like this. you can get carbocation. And product like that, plus you're going to get a bunch of stereoisomers of that. Because that carbocation is flat, so you can have addition, like the nucleophile can attack at the top or the bottom. So it's 50-50 chance, so you're going to have a pair of enantiomers. Also, the hydrogen, when it goes on, can go either in the front or the back. So there's going to be a 50-50 chance of that too. So you have a total of 4 stereoisomers, which would be RR, RS, SR, and SS. And all of them can be formed. So we would say that this is a reaction that's not stereospecific because it doesn't produce one stereoisomer, it produces a bunch. And we wouldn't call this syn, we wouldn't call it anti. We would say that this is a mix of syn and anti because that carbocation, there's not really, it doesn't direct the stereochemistry to be a certain way. But we have a carbocation intermediate. We called this mechanism ADE2. And because it's a carbocation, you can have rearrangements depending on the carbocation that's formed, and so on. Great. Then we did hydration of an alkene. Started with sulfuric acid and water. 50-50 mix of the two. Would go through a carbocation intermediate to give you the Markovnikov alcohol. If you had a situation like this, you'd make this carbocation, which could rearrange to a carbocation like that. So both of these alkenes will give you the same major product. So this is also ADE2. There are rearrangements possible. Okay. We have carbocation, so rearrangements like you see in the bottom case. We have Markovnikov addition, so the hydrogen goes to the less substituted side, OH to the more substituted side. Very similar to the previous reaction, very similar to the previous mechanism. And so it gives you a Markovnikov product that may have rearrangements. So we had 2 other variations of the addition of water, of hydration. One was oxymercuration demercuration. Mercury acetate, mercury 2 acetate. OAC is equal to O. It's acetate. So when you see OAC2, that's an anion, so it's negatively charged. Second, we treated it with NaBH4 NaOH. And what this will give is the Markovnikov product with no rearrangements. No rearrangements. Markovnikov product. And not stereospecific. meaning not anti, not syn, get a mix, get a bunch of stuff. So this is, in terms of the products you get, the same as step 3 in many cases, but where a rearrangement might take place with 50% sulfuric acid, you won't get that under these conditions. This might be a better set of conditions if you are worried about rearrangements. Changing your carbon skeleton, which is not what you want necessarily in a reaction. 5, we also had a variation that looked like BH3THF. THF is a solvent, right? THF looks like this. Tetrahydrofuran, 5-membered ring where one atom is an oxygen. This will form a complex with BH3 to stabilize it. And this is basically a source of BH3. And this takes place in 2 steps. We add the borane group, BH3, and then we oxidize it. H2O2 NaOH. It's called hydroboration oxidation. Like that. This has no rearrangement. This one is anti-Markovnikov. And it is syn addition. So that means if you have an alkene like this, for example, it's another set of conditions which is the same as BH3THF, which we would say is B2H6 diglyne. Same thing. What this product would be syn addition. So the hydrogen, if it goes in front, the OH will also go in front. And the CH3 that was originally there will be going back. So the OH goes syn. Yeah, Lizzie.
I was going to say, does the anti-Markovnikov just mean it's the least substituted?
Yeah, so it means the OH would go on the less substituted side and the hydrogen on the more substituted side. I kind of feel like I'm missing one. Am I missing one? No, I think I got them all so far. The next one we did was addition of Br2, bromination. Call that 6. I'm not going to say Br2, X2. So typically for addition of X2, we need a nonpolar solvent. Usually we would use something like hexane or dichloromethane, which is CH2Cl2. These are nonpolar or weakly polar solvents. And the addition of this is anti. So the mechanism we would have would look like this. You have, let's go cyclohexene. We'll use Br2. Put in all our lone pairs. And this is the one that had that kind of funky first step where we had a lot of arrows. So the first thing that happens is the double bond, pair of electrons in the pi bond, attack the bromine that's closest to form a carbon-bromine bond, which we could draw like that. At the same time, one of the lone pairs on that bromine come and attacks one of the 2 ring carbons, part of the double bond. We'll say like that. Also, the BR-BR bond breaks, and those electrons go on to one of the bromines. Like that. So there's 3 arrows you draw, all in that first step. And we need to draw a product that makes sense. So that Br now has 2 bonds, 2 carbons. It has 2 lone pairs left. And the Br that has left has an additional lone pair and a negative charge. We have hydrogens that were there before, and the bromine will have a positive formal charge. Okay, so it makes this weird looking intermediate, which we call a bromonium, which, as you can guess, is probably not super stable because you have a 3-atom ring and you have a positive charge on an atom that's somewhat electronegative. Bromine super doesn't like to be positively charged. It doesn't have to be. So we have a nucleophile here, which is the bromide floating around in the background. What it can do then in the second step is come and attack there and do essentially an SN2. And what that would do is push the bromine off to the left. And because SN2 is always backside attack, that second bromine has to attack from behind. So second bromine comes from the other side. So you get the trans product, which is why we say the addition in this case is anti. 2 bromines end up on opposite faces of the original starting double bond. And that's the mechanism right there. 2 steps, lots of arrows in the first step. Second step is more straightforward. Second step is just an SN2. But this mechanism is nice because it explains why you can only get the trans product, which, if we didn't know the mechanism, wouldn't make a whole lot of sense. Especially if we thought this went through a carbocation or something like that. So those bromoniums are more stable than carbocations. They don't rearrange like carbocations, so they're a little bit easier maybe to manage, to deal with. And yeah, that's where we're at, I think, at this point, which is great. No, that's not what I wanted. This is what I wanted. The next reaction we're going to do is number 7, and number 7 is almost the same as number 6. Remember before when we did addition of Br2, we did addition of Br2 in a nonpolar solvent like hexane or dichloromethane. Those solvents are just sort of dummy solvents. They don't really do anything. They don't strongly solvate anything. They don't stabilize intermediates, anything like that. The only reason they're there is so that the reagent, the bromine, and your starting material can come into contact with each other. You need a solvent that can dissolve them both, and because Br2 is nonpolar, you need a nonpolar solvent. So hexane is about as nonpolar as you can get. A little bit more polar is dichloromethane. Chloroform might be another one you might use. Chloroform is CHCl3. Chloride at one point would have been a great one to use. CCl4. Carbon tet, problem with that is it was banned in the 90s by the Montreal Protocol because it's a source of chlorine in the atmosphere, which destroys the ozone layer. So it was banned along with freons and a bunch of other things. So you can get this still. We actually have in our department a couple of jugs of this stuff that were purchased back in the 80s, and we treat it like gold because to buy a 4-liter jug of that back when we bought it in the 80s, I wasn't here then, of course, but back then a jug would be like a couple of dollars, where now the same jug's like $1,000. And of that $1,000, like 990 of those dollars are taxes because they just put crazy taxes on these, so people won't buy them anymore. And yeah, so you see this solvent used quite a lot for this bromination reaction in older papers, older texts, because this was a more common solvent at one point, but we use different things now, which in some cases are not as good for various reasons. One nice thing about carbon teth, there's another reaction that you'll do, maybe in organic too. It's a bromination called NBS bromination, yeah?
Why don't you want that solvent?
Because it destroys the ozone layer. Yeah, yeah. Chlorine atoms, it's a chlorine atom source if it gets up into the atmosphere. So, yeah, it's a good thing, but you might actually see it depending on examples that you come across. You might see CCl4, just a non-polar solvent. It's very polarizable. It's actually pretty good at dissolving things. It's got a lot of nice features, but yeah, ozone layer. So what if we instead don't use one of these non-polar, non-reactive solvents and we pick something like water? And as we learned already, water can be all things to all people. It can be a nucleophile, it can be a base, it can be an acid. It does a lot of different things. I guess the one thing it really doesn't do, it's not an oxidizer or a reducer. You can oxidize and reduce it, but it's hard. But it's easy to do acid-base or nucleophile chemistry with this. If you pick water as the solvent, when you do bromination, you still get anti-addition, you still get one thing added to both sides, but you end up getting a Br on one side and an OH on the other. This molecule is called a halohydrin. Okay, it's a vicinal halohydrin. What does vicinal mean? Adjacent carbons. Geminal is the same carbon. Yeah. So the Br and the OH, halo is a halogen. Hydrin means water, OH. They're on adjacent carbons because they're vicinal. And this is the product that you get. So it's kind of like Br2 addition. We put a Br on both sides if you're in a nonpolar solvent, but when you're in water, OH adds to the other side. So here's an example. We're using Cl2 this time in water. So this is what would happen if you went swimming in a swimming pool and there was chlorine in the swimming pool. There's water with chlorine in it. And let's say you had something with an alkane with a double bond in there. This reaction could happen. So let's say there's a dye in your bathing suit that has alkenes in it. This could happen and your bathing suit might lose color as a result. So this is a way that chlorine could destroy color in a fabric or a dye or something like that. And we know that happens if you swim a lot. So yeah, chlorine will add, chlorine goes to one side, OH goes to the other, and notice that the product here is trans. So it has the same stereochemistry as if you just added Cl2 or just added Br2 in a nonpolar solvent. Okay, so it certainly looks similar at this stage as the previous reaction. The mechanism actually looks very, very similar as well. Mechanism looks like this. The halogen comes in. You have that 3-arrow action. You make the halonium ion, like before. The nucleus back from the backside to do the SN2. The mechanism here is identical to last time. The difference is if you're using water as your solvent, water is there in very high concentration because it's the solvent. There's a lot of it around. It can act as the nucleophile instead of the Cl-. So the water can attack on the opposite side, and it just does a regular SN2, same reaction as if it was chloride, except now there's a different nucleophile, and water picks up the hydrogen here. There's an arrow missing. There's an arrow, should go like that as well, and you end up with your product over here. Identical mechanism as before, only difference is we have water as our nucleophile. Cool. So look at an example like this. Here's an example of an alkene that's asymmetric, meaning the degree of substitution is different on the two sides of that alkene. One has 2 alkyl groups, the other has 0. It's geminally dye-substituted. We're going to treat it with Br2 and water. And you can imagine the regiochemistry here. There's two different ways this could go. You could add the bromine to the more substituted side, or the OH to the more substituted side. And if you think about it, it's almost like the Br adds first, and the OH adds second. It's not really a carbocation mechanism, though, so we can't really apply the same kind of thinking. But what happens is, experimentally, what we see is the OH will end up on the side of the double bond that was originally more substituted. That means B is going to be the major product and not A. So it's kind of like Markovnikov's rule, where the thing that adds first goes to the less substituted side, and the thing that adds second goes to the more substituted side. And we're going to look at why this is the case. It turns out when you have this halonium ion intermediate, and you have your nucleophile water floating around underneath, it's deciding which of these two carbons it wants to attack. Right? It can attack the right side or the left side. It turns out that that intermediate, we draw it like the charge is on the chlorine. But in truth, that charge is sort of shared over all three atoms that are in that ring. You can't really draw that well with Lewis structures, because Lewis structures force us to have electrons as little dots in one place, in a bond or in a lone pair, not shared, right? You can't do that with Lewis structures. But in reality, it is shared. That positive charge is not necessarily shared equally over those two carbons. In fact, it's shared more. There's more positive charge on the carbon that's more substituted. And the reason it wants to put more charge there is because it's more substituted. More alkyl groups can stabilize putting more charge there. So the water wants to attack the carbon with more charge. So it turns out this one will have more positive charge. In the transition state, which looks like this, there's going to be positive charge on that carbon as well. And so the best outcome is for the water to end up attacking the more substituted side. Chlorine ends up on the less substituted side. Okay? Some lone pairs in that chlorine. So it's the energy of the transition state that determines which step is fastest, not actually the energy of the intermediate. So yeah, of these two possibilities, this one is preferred because that puts more positive charge on the carbon that's more substituted. Cool. It might seem opposite to what you'd expect, because this step is like an SN2. And SN2, we're told, doesn't happen on tertiary centers, right? So shouldn't it go for the less substituted side? Well, yeah, if this wasn't positively charged, if this wasn't, if it was neutral like most SN2s we've seen, but in this case, it's the other way around. It'll go for the more substituted carbon because there's more charge there. Great. So we added one reaction, which was the same as a reaction we've already done, except a little bit different of a nucleophile. I want to do one more example. Let's say we do this. Let's say we do I'm going to trick you. I'm not going to use a nonpolar solvent, and I'm not going to use water. I'm going to use ethanol as a solvent. What product would we get in this example? Well, first thing that would happen, let's put all our lone pairs in on bromine. First thing that would happen is that would attack the Br. Those would attack there, and those would go there. That Br floats away. And we have ethanol as our solvent. We know ethanol can be a nucleophile, can't it? So we can come in and attack. And we don't like to have final products with charges on them, so we can neutralize that by taking in a second ethanol, and it can remove the H plus. And ethanol can be our nucleophile. So really, the first thing that adds will always be the Br or the Cl. The second thing that adds can be just about anything. So if you want, imagine you did something like this. We're going to do it with Br2 and water, but we're going to load it up with a really strong nucleophile, cyanide. This could give you a product that looks like this. In fact, this product wouldn't last very long, would it? Because this is a primary alkyl halide in the presence of a strong nucleophile, NaCN. It's going to react again. Give you something like that. There's an unusual product, eh? So products like this, this is where I think understanding mechanism becomes very important. Because if you understand what's going on in this mechanism, the bromine goes first, then the nucleophile comes in, and what's present in solution, cyanide's a better nucleophile than water. So if you have enough of it there, it can compete with water. And then realizing you have a primary alkyl halide as a product, so then cyanide can come and attack that too, put a second one on. This is something that you can reason out if you know the mechanism and what's in there in solution with it. But if you're just memorizing reactions, you haven't seen this before, if you memorize this same reaction with no NaCN, there's no way you would have predicted this product. Now, because you know the mechanism, you can throw any nucleophile in there and predict what will happen as an outcome. Isn't that great? Okay. Cyclopropane synthesis, we're going to cut. Okay. It's fun. It's a neat reaction. You get to use cool things called carbines, but for another time. This is a reaction which is kind of niche, I guess. You don't often want to make cyclopropanes, and when you do, it doesn't connect well with the other reactions we've done in 6 and 7. So we're skipping that one this year for the sake of time and understanding the other reactions maybe a little better. So we're going to jump right to 9, which is synthesis of vicinal diols. So synthesis of vicinal diols can be achieved in 2 different sets of conditions. Basically what it does, we have already seen a vicinal halohydrin, and we've seen a vicinal dihalide. Vicinal dihalide comes when you add 2 bromines by adding Br2 in hexane. We're going to do the same thing, except we want 2 OHs, vicinal, 2 OHs next to each other. And this can be done by treating it under either the first set of conditions, which is osmium tetroxide, OSO4. Osmium tetroxide is a fairly toxic compound. Osmium is one of those metals you don't come across that often, but we can use it here. And then we use sodium bisulfite, NaHSO3, and water in step 2. And that breaks down the intermediates to give you 1,2-propane diol. I'm going to show you a bit of the mechanism here, but I'm never going to ask you to draw it again. This is not one of the mechanisms you need to be able to write out. You can get the same product using KMNO4 permanganate in the presence of base if it's cold. And we're going to look at what happens if it's hot. So what happens with the osmium tetroxide or the permanganate, basically same mechanism, is the osmium tetroxide comes in, it forms this weird kind of 5-atom ring with carbon-carbon, oxygen, osmium, oxygen. It kind of just lands, and the two oxygens kind of form bonds with carbons. Give you this thing. And that is broken up with sodium bisulfite, NaHSO3. NHSO4 is bisulfate, so this one's bisulfite. And because of the way this added, it kind of added both together at the same time. You end up with the cis product, and the addition we say is syn. Okay. That's kind of it. That's what we really want to say for this. You add the same thing to both sides, so like Markovnikov or anti-Markovnikov isn't really a thing. Rearrangements aren't a thing. Syn addition, so it'll give you a cis alcohol if it's on a ring. Let's do an example. Seems too early to leave this one. No, this isn't step 1, step 2. I think this is all together. But it's cold. What this will do is it will add OHs to both sides. It'll add them both to the same side. And this is an example where the stereochemistry does matter. Syn addition would give you a different product than if it was anti-addition. So the way I would draw this is I'd put the OH here in front, the hydrogen in back. On the other carbon, the OH goes in front, and the hydrogen goes in back as well. So you get a product that looks like this. And notice how the two OHs both came from the top. They both come from the top. It'll give you this compound, which gives you, what, S, and this one is S as well. Or RR. This would be produced in 50%, 50%, which is racemic mix. Because this alkene is flat, trigonal planar on both carbons. There's no preference for the front face or the bottom face, the front or the back face. So just depending on where the permanganate happens to land, front or back, you'll get either the RR or the SS. And you'd expect statistically to get like a 50-50 mix of these two. So you get a racemic mixture. Fun reaction. Good. By the way, like, we're not going to just spit these out and then we're going to come back. We're going to look at examples with these. I think we'll have a good amount of time to do review before the exam. Although we don't have a lot of classes left, right? What's the last day of class? Like the 11th? Is the 11th a Friday?
Yeah.
So we have 2 more classes this week and 3 next week. Wow. I won't be doing new material on the last day. So, I mean, we'll go to the 11th. We'll go to the last day. But, yeah. I expect to have long since finished what we need to finish.
Is our last assignment this one or the next one?
So what's the assignments is the last one will likely be this one, but we'll probably post, if we go into the next chapter, we do unit 9. Unit 9 is like super short, like it's a 1-class chapter. We might post an assignment, but if we're not going to make an assignment due after the last day class. So sometimes we post assignments and it's just do it for practice, but yeah, it won't be part of your mark. Oxidative cleavage of alkenes. So let's say we're going to use potassium permanganate with base and water again, but in this time we're going to heat the thing up. Okay. In this case, we're going to heat this up. We're not going to do it cold. So this is exact same conditions as before, but it's hot. What that does is it breaks that carbon-carbon double bond and oxidizes both carbons on both sides. And it oxidizes them all the way up to carboxylic acids. Okay. In this case, where we have a di-substituted alkene on the left side, it can't go to a carboxylic acid. It oxidizes it up to the maximum. So it oxidizes it to, in this case, a ketone. And if it's CH2, it goes all the way to CO2. So there's 3 variations here for oxidative cleavage, where if you have, let's say you have an alkene like this, it will oxidize to ketones. If you have something like this, same conditions, to get something like that. If you have a methylene, a CH2, the left side here goes to the ketone, the right side goes to CO2. So yeah, it cleaves the bond. It breaks the molecule in 2. Here's an interesting example. What if you have this molecule? What would happen here? Well, we cut the bond. Like that. That's kind of an ugly way to draw a molecule. Count the carbons. 1, 2, 3, 4, 5, 6, 7, 8. 5 there. 8. 1, 2, 3, 4, 5, 6, 7, 8. That's how we would probably more likely draw this, like a zigzag. So this is what the product of that reaction would be. If instead you had this one, you get this. So this reaction is called oxidative cleavage because cleavage means to cut. So we're cutting a bond, right? So we're cleaving it into 2 pieces. If it's on a ring, of course, you have to make 2 cuts to get 2 separate molecules out. Cut it once, you're just opening the ring up. Might call that a ring opening reaction. Okay, that's oxidative cleavage. There's a second way we can oxidatively cleave a double bond as well, and this is using ozone gas, O3 minus. So it's just O3, O3. O3 is a very strong oxidizing agent. And what it can do is react with alkenes to make this weird intermediate through a mechanism you're not responsible for, to make this thing called an ozonide, which I don't like the name ozonide. The reason is that IDE, typically means negatively charged. Like chloride is a negatively charged chlorine, right? Alkoxide is a negatively charged oxygen. This is not negatively charged. This is neutral, but we call it an ozonide anyway. And then you need something else, like zinc will do it. Dimethyl sulfide will do it. Zinc is a less smelly variation of dimethyl sulfide. And what it does is it turns it into ketones or aldehydes or whatever. So there's a bit of a difference here. If you have, I'm going to go back to my thing here. If you have an alkene that looks like this, and you use the KMNO4, with heat, that's going to give you aldehyde on one side, OH on the other side. You're going to get the carboxylic acid. If you did the same thing, ozone, and then we use zinc and water, it gives you a ketone, same on the left, but the right-hand side gives you an aldehyde. So with ozone, it's simpler to pick the product because ozone, it always does the same thing. Ozone, what you do is you cut the bond, separate, cut it, separate it apart, cap them with oxygens, and you're done. You can think of, same thing. Cut it. 1, 2, 3, 4, 5. Cut it, cap it with oxygens, and you're done. So ozone is actually really good at, well, obviously destroying double bonds, but it's good at, like, living things have double bonds in us. So ozone is really damaging to our tissues. It's damaging to microorganisms as well. It's actually really effective disinfectant. And when they bottle water, what they do is they take water and they bubble in ozone gas and cap it. And the ozone is capped and sealed. Any germs that are in there will be killed, be oxidized by the ozone that's in there because of reactions like this and other ones, and kill the microorganisms in there. And because it's sealed, no new microorganisms can get in. And then the ozone over time will break down into oxygen gas. So when you look at bottled water, one of the ingredients is often ozone. But typically, I mean, unless you take it fresh off the conveyor belt as soon as it's bottled, there won't be any ozone in the bottle by the time it gets to the consumer. Great, so ozonolysis works well there. Cuts it in half and just adds oxygen. So it doesn't make carboxylic acids. It doesn't make CO2. If you had a CH2, it just becomes formaldehyde. Okay. Here's some examples. So an example like this, where it's a CH2, it still has the CH2 in the product. Just cut the bond, put in oxygen. This is an example of a ring opening one, like one we just looked at. So two ways of doing this. The ozonolysis way is a little bit simpler because there's sort of less to remember, but both cut it, open it up, and then oxidize the carbons on either end. Cool. That's as far as I want to go today. We have a couple more reactions to finish up, but not too much more. I don't think we're going to get to Unit 10. Unit 10 is a really nice one because it has complementary reactions to the ones you get here. Because, like, you know how we did 3 variations of hydration, and then we had, you know, making the halohydrin. We use halohydrins in Chapter 10, so it's like nice that we can make them then, come back to them. The other one is we just did syn dihydroxylation, like making vicinal diols. You can make trans ones in Unit 10. Some reactions there that are nice that we're probably not going to get to. But if you take organic 2, then maybe you'll have a chance to see some of these. Okay, we are good for today. We learned a couple more reactions. I guess we're up to 10 or so from this unit, and a couple more, and we'll be done. We might have one class left maybe in this unit, not much more than that. All right, say goodbye to everybody. Stop recording.